In today's video, we are going to continue our study of DNN architectures. The last video we studied CNN, and today we'll continue on RNN and auto encoders. CNN was designed for 2D and 3D image data, and RNN in particular is specifically designed for sequential applications, for example, text recognition, speech recognition, and so on. Each one of them have the property that there is a long-term dependence in words in this compared to images in which for object recognition, we just have to look at for the object in the same image. In feed-forward networks, and CNN is a part of it, output of the network at time t, which is denoted by yt, depends only on the input to the network at time t, that is xt. The same thing holds for any node inside the network. Whatever the output of the node at that time is, depends only on the input at that time and not on past or future of the inputs. In this particular case, output yt depends only on xt and not on xt minus 1 and xt plus 1. Here t we are denoting time in discrete values, like you can take time to be t is equal to 1 to 3 and so on. In RNN, the recurrent neural networks that we are studying in today's lecture, there are loops and cycles, unlike in feed-forward networks where there are no loops and cycles. Now, because of loops and cycles, we can have, these can capture long-term dependencies in the data. And that is done by each node, the hidden node in the network has a hidden variable, which we will call state of the node. So state keeps the past information, which will be used for output at time t as well. So at time t in RNN, input to the network or a node is xt at time t, output is yt at time t, and ht is the hidden state at time t, and ht is equal to sigma h. Sigma is the activation function of whxt. Xt is the input, and wh is a weight vector. So whxt denotes the inner product plus another weight vector, multiplied by ht minus 1. Ht minus 1 is the state of this node at time t minus 1 plus bh, which is a constant. And the output yt of the node is sigma y, which is another activation function, and this is a function of wh in inner product with ht that we have the state defined above, plus b gamma. So if you look at these two equations, the past dependencies in the node is captured by the state ht, and yt being a function of ht now depends not only on the xt but xt minus 1, xt minus 2, and so on. We have learned before that feed-forward networks can approximate any function f from Rn to Rm arbitrarily closely. Now, RNNs, because of the loops and the ability to depend on the past, can actually approximate any continuous or discrete time dynamical system. So dynamical systems are the systems evolving in time. So RNN can in fact approximate a dynamical system, while F feed-forward networks can approximate only a function. And RNNs are also related to finite automata, which again are some kind of dynamical systems. Like CNNs, RNNs, deep RNNs in particular, are exponentially better than shallow neural networks. That means they can represent functions and dynamical systems much more exponentially, more efficiently. Like in feed-forward networks, where for learning we have backpropagation algorithm. For RNNs also there is a similar algorithm, and it is called backpropagation through time. So this has similar features as backpropagation in feed-forward network, in the sense that in learning, when we are using when we need the derivatives of the output function with respect to the weight vectors, you can do back propagation to compute the different derivatives. So similarly here in RNNs, we have back propagation through time. And in RNN, just like in feed-forward networks, we can also use regularization. In other words, remember regularization term is lambda into norm of W square, where W is the vector representing the weights in the networks. Similarly, as for backpropagation, uh, in PPTT also, the system suffers from vanishing and exploding gradients. In other words, whenever the gradients can increase or decrease, then it can cause problems in the networks. And similarly, as in backpropagation, the solutions for this problem are you clip the gradients. If the gradient too large, you clip at a certain level, and similarly for a very negative large gradient, you clip at certain level there as well. And scaling of the data before you enter it. RNNs aim to retain useful past information because it is supposed to represent the dependencies with past. However, keeping all the past data is not efficient because it requires too much storage. Therefore, the important thing is that you want to retain the relevant information that is needed now and in future, and forget the past information to keep limited storage requirements. This forgetting in RNNs is done by internal state. Remember, the internal state was HT. Is if it is erased, then the past will be forgotten. To retain this kind of uh, attractive properties, that you keep some relevant information and not all the past information, a new architecture, LSTM, has been designed within RNN. LSTM stands for long-term, short-term memory. So in these architecture, you will keep some long-term memory, which is the relevant needed information, and of course the short-term memory. It has forget gate, input gate, and output gate. Forget gate helps in forgetting the past information. GRU is a simplified version of LSTM. It has fewer gates than LSTM. LSTM, it has been found that can be a quite complicated architecture, and therefore, if it is more complicated, that means that training it requires longer time and more samples. So simplified version, GRU, gated recurrent unit, it has fewer gates therefore than LSTM, and therefore is computationally lighter, as well as it learns faster than LSTM. So as a result, when there is limited data, GRU performs better than LSTM. However, as you get more and more data, eventually LSTM will start performing better than GRU. In this video, we are not going to explain LSTM, but only GRU because of the reasons mentioned above. In GRU, there are two gates. There is an up gate and a reset gate. In up gate, the output is ZT, which is equal to sigma, that is activation function, of WZ. This is a weight vector, which is taken inner product with ht minus 1, ht, remember, is the state of the node, and xt the current input. So zt we are defining some intermediate thing which depends on ht minus 1 and xt. It captures long-term dependence, as we will explain below. And the other gate is reset gate. Its output RT is equal to sigma WT. This is WT here, another weight vector, which is taken in a product with HT minus 1 and XT, just like above. It captures the short-term dependence. We further have an intermediate hidden state, HT tilde, which is hyperbolic 10 of W dot RT, and there is a star sim operation where the vector RT and the vector that we have HT minus 1, you are taking their products component wise, RT star HT minus 1 and XT. So HT tilde is hyperbolic 10 of W multiplied by these two vectors. If R is short, then in HT tilde, the contribution of HT minus 1 will be small, and there will be more contribution of the current input. Therefore, this will represent short-term dependence. Now, the hidden state HT is equal to ZT star HT minus 1, the previous state, plus 1 minus ZT star HT tilde. Remember HT tilde given above. If RT is small, then HT tilde has dominant contribution from XT. However, in HT, we have a ZT star with HT minus 1 and HT tilde as well. Now, if ZT is close to 1, then contribution from HT tilde is less, and therefore the contribution from XT is less, and there will be more contribution from the previous state HT minus 1. This represents long-term dependence. GRU and LSTM, so these are used in NLP, natural language processing, and time series analysis. And as we explained earlier for RNN, that we have a backpropagation type of algorithm. However, the challenge is here in the learning of RNN, because of long-term dependence, are more than in the feed-forward networks like CNN. Therefore, sometimes CNNs are also used for time series and speech recognition, which were originally being the applications for RNN. And CNN can have some dependence. It has limited dependence compared to RNN, and in some applications, that dependence is enough. And for such time series and speech recognition applications, people have found that, in fact, CNN can actually be better than RNN. Next, we discuss here the autoencoder architecture. In autoencoder, there are two neural networks. One is encoder, the other is decoder. Encoder compresses the input information X, which may be a vector in RD, to a smaller dimensional Z, which has much less dimension than D. And this compression is done by encoder in such a way that minimal useful information is lost. The advantage of reducing the dimension from X to Z with minimal information loss is that now if we work with Z, for whatever reason, the computational load will be smaller. It requires much less storage to store Z than X. And if we have to communicate this information from one place to another place, instead of communicating X, transmitting Z will require a lot less communication resources. So there are many applications where compressing information from X to Z without much loss of information is very, very useful. And this autoencoder is used for that. This operation of reducing dimension from X to Z with minimal loss was previously done by feature extraction. But in feature extraction, human intervention was required and domain knowledge of the experts was needed. But in this case, using autoencoder, we are going to use deep neural networks and no human interaction will be required. So that is the advantage of this compared to the previous feature extraction techniques that people were using. So encoder, we are going to go denote by mapping phi, that is from RD to RD prime, where D prime is much less than D. So via using this mapping phi on the input X, we obtain Z, the compressed lower dimensional vector. And the decoder in the same way is denoted by another mapping psi, which will take this compressed vector Z and try to recover X from this, which we are going to denote by X prime. We are going to choose phi, the encoder, and psi, the decoder, in such a way that the norm between X and X prime, the difference between them is minimized. Phi and psi, the encoder and decoder, can be, and in this case will be, designed by deep neural networks. So this way there are two deep neural networks, one designing the encoder, the other designing the decoder, and which does the operation of compressing data after the encoder. This architecture has become popular in communication systems and natural language processing as well. In communication systems, because communication systems have encoders and decoders, similar kind of architecture traditionally, and therefore this architecture of autoencoder containing encoders and decoders is very appealing to communication people. We end this lecture today at this point, and we will continue further later on. This completes our study of introduction to deep neural networks. More advanced features, as we have mentioned earlier, will be discussed in the advanced part of this course. Thank you very much.